Okay, in today's lecture, we are going to cover what is called the Schlieren imaging. So, Schlieren imaging is a very commonly used technique that is useful in many applications. Okay, so today's lecture notes are courtesy of Dr. L. Venkatkrishnan of CSIR NAL and also from Galseat Caltech. So Schlieren imaging is a very promising technique where we basically use this technique for multitude of applications whenever there is an inhomogeneous transparent media is involved. And we will see what that means throughout the duration of this particular lecture. Okay. So, but the Schlieren imaging, is an extremely powerful tool. So, where do we see such occurrences? So, you have seen stars which actually twinkle. Okay, so because it twinkles because the atmosphere is inhomogeneous. So what happens is that disturbances due to turbulence, change in air density leads to a change in refractive index. And because there is a change in refractive index, the rays of starlight actually bend and the wavefront of the light is wrinkled. As a result of that, there are fluctuations that starts to happen. So on the time scale of the atmospheric disturbances, the fluctuations appear. Therefore, you see the stars twinkle. So, but this is a celestial event. And because it's a celestial event, can't we do the same thing and use it for our own purposes? So can we use the change in refractive index, which is linked with the density change, and we can develop density-based optical techniques for doing multitude of applications. So that is, I think, what is the main crux of the story is going to be for the next few lectures. So this is a celestial, very commonly occurring event. So if you look at a slightly historical aspect of this, Robert Hooke was a guy who is called the father of optics of inhomogeneous media. He basically invented the Schlieren method. He discussed that the refraction of light due to density variations causes twinkling of stars, mirages in the desert, and in convection in fluids. So let's take a look at this candle flame. So there is a candle which is burning. As a result of that, the air which is around the candle gets heated, common occurrence, and then you form a plume. That means the air loses its density, it becomes lighter, and it rises. So the rest of the fluid, which is right around here, okay, are basically fluids which are at room temperature. As a result of that, what happens is that if you go from the center to the edge and beyond, both ways, right side or left side, you have a change in density. So as you can readily see that the density rho 2 is less than rho 1 because rho 2 is lighter and the density is lower, therefore. That's why it rises. That's why you have a plume. So naturally, you have a change in refractive index from the center all the way up to the edge because there is a change in density which has led to a change in refractive index, which is written as the partial of n with respect to x. Now, the refractive index n2 actually has a lower refractive index than n1. That means the colder fluid, which is the fluid which has got the higher density, therefore has got a higher refractive index as well. So these are the relationships that are given here. This can also have a dependence in the x direction. If x is into the board, into the plane, so it can have a variation in that direction also for a 3D structure. Okay, so this is the crux of the story. Okay? So what Christian Huygens did was that he looked for stria in glass banks and he grinded them to make lenses, which is the most important discovery, because without these lenses and mirrors, we would not have any optical measurements at all. And he had an optical shop testing which tested the quality of this glass. Now, John Paul Marat, he invented what we call the helioscope, which is a sun-powered shadowgraph projector. These nice images that you see, and he was the first to publish these shadowgraphs. So, unfortunately, the French Academy of Sciences rejected his work, and he joined the French Revolution. Science faces a lot of problems, so to say. So this problem is naturally one of them, and it is not something that one can. There are a lot of hurdles in anything that you do. So, but these are some of the historical aspects. So then, of course, there was Leon Foucault. He was the first to use a cutoff, mask, top, filter, knife edge, basically brought more quantification to the Schlieren aspect. And he was the first to test the quality of the telescopic mirrors also. Foucault, you have heard the name from his pendulum experiment also. Then August Toppler, he reinvented the Schlieren method. What he did was that he used high-speed imaging, coined the word Schlieren. In German, Schillerie refers to streak, striation, or chord. And he also laid down the procedure to set up the Schlieren. And he was also the first to study shock waves using Schlieren. For example, this is a shockwave image. This is a supersonic projectile. Okay. And you can see that there is an attached shock. Okay, front of it. So this clearly says that there is a sharp, shock waves do have sharp density changes. As a result of that, you have a large, you have changes in the refractive index, not large, but so that is what is shown over here. Then, of course, there was Ernest Mach. He used Schlieren to measure the wave speed. And he made very crucial discoveries in coining the Mach number, which is basically the ratio of the velocity of the projectile divided by the velocity of sound. So naturally, this number, if it is less than 1, it means subsonic. And if it is greater than 1, it means supersonic. That means the velocity of the projectile or the object is much more than the velocity of sound. Now, to verify these claims, okay, there has been work on high-speed spark Schlieren of a supersonic projectile. There has been a test on the flow exhausts and also measurements in supersonic tunnels. The Mach disk and other things came into picture right at that point. So some more aspects is that Julius Reinberg used Schlieren to distinguish between transparent objects instead of chemical staining. And he was the first one to use color filter, which basically laid the foundation for color Schlieren. Then, of course, there was Mach and Schneider, and they devised the interferometer, which is basically uses optical path difference. And then Hubert did theoretical background for Schlieren imaging, and he used it for different ballistic development. So you can see here a bullet penetrating through a candle flame. You can see the large scale structure of the candle flame and the very fine structures of the bullet or the trail that is left behind by the bullet. So you can see the granularity or the details that we can extract just by looking at it. On the other hand, the shock wave in a diffraction around a wedge, for example, this you can see. Here also you can see large scale structures, small scale structures. So all these things are clearly visible, when you are dealing with this kind of framework. All right. So one can see it. So it has developed over time. It has developed over multiple people, and we have gotten better with the advent of high-speed imaging, with the advent of more sophisticated and optics and more high-quality optics. I might add, we have proceeded a long way from where we were, from 2-3 centuries ago. So now we go into a little bit of mathematical details. So how do we define refractive index? So refractive index is nothing but the velocity of light, divided in vacuum, divided by the velocity of light or the speed of light in the medium. The velocity of light in vacuum is 3 into 10 to the power of 8 meter per second. And the speed of light in the medium is whatever is the speed of light in the medium is going to be. Now, normally the refractive index will be greater than 1 because, that's the highest velocity that you can have in a particular medium is vacuum. Okay? The air, for example, has a value which is 1.000292. So the first significant digit comes after in the fourth place of decimal. So this is the the speed of light in air. So the good part is for gases there exists a linear relationship between the refractive index and the gas density. So they are related as n minus 1 is equal to k into rho, where 1 is subtracted just because of this vacuum issue. So n is the refractive index of that particular medium, and n minus 1 is called the refractivity, and rho is the gas density, and k is the Gladstone-Dale coefficient, which is about 2.23 centimeter cube per gram. This is cube, centimeter cube. Okay. So you can readily understand that, there is a linear relationship. So you think that, oh, things are very good, because linear relationship is what helps, because you don't want relationships to be power laws and stuff like that. You want them to be linear so that you can extrapolate them to higher values or interpolate them. You can do all kinds of stuff. So this is good news that you have a direct correlation between the density and the refractive index, and the refractive index is all about the velocity of light in the two mediums concerned. But to make the story a little bit difficult, refractive index is a very weak function of density. That means here you can see that the density increases from 1 to 2, and the refractive index hardly shows any increase. Okay? It goes to about, say, 1.004 from about 1.0029 something or 22 something. So this is a very minuscule increase in the refractive index, okay, for a 2 times increase in density. To make matters worse, if we plot now a large variation in density, so here you can see the density is plotted from 1 all the way up to 100. So there is 2-order change in the value of density, but this 2-order change in the value of density only leads to about 2.3% increase in n. The n increases by only 2.3%. So even for 2 orders change in the density. Now, this poses a problem because you have a very large variation of one parameter and you have a very small variation of the refractive index. And density variation by 2 orders is not obvious in any, for example, in a candle flame where you have this plume which rises along with that around the candle. That does not have a density variation which is 2 orders. So there is a minuscule change in refractive index for a very large change in density. So this means that you need to have very, very sophisticated and sensitive optics. So let's look at the next one. So how the light actually propagates through an inhomogeneous media. So for example, so there is a planar wavefront. That means all the rays are actually parallel to each other, and not only parallel, they traverse by the same distance over a certain period of time. So that means this particular material does not have any refractive index change. That means there is no density change. This impinges, and then this is where in this particular medium, right after this boundary, you start having a change in the refractive index. So how does the refractive index change? It changes in a negative fashion. That means the gradient of the refractive index with respect to y is less than 0, which in other words means that as you decrease y, your refractive index n is actually going up. Okay, so the refractive index here, the lower part of this particular figure, is actually higher than the refractive index at the top. So that means this particular medium is highly homogeneous and it has got a refractive index change which is given by this gradient. Now if you look at it, now the top ray, if you look at it, or any ray as a matter of fact, it traverses some distance which is delta z in a small period of time which is delta t. Now delta Z is given as C into delta T, where C is the local velocity of light in that medium at that particular location. So in other words, you can say that C is C naught by N, where N is the local value of the refractive index, where C naught is the velocity of light in vacuum. Okay, this is multiplied by delta T. Now, if we consider it for two rays, which is Y1 and Y2, you can see delta Z1 is given by C naught divided by N1 into delta T, and delta Z2 is given as C naught by N2 into delta T. Now, since your N2 is greater than your N1, because that's what we said, that the refractive index actually increases, that means the medium is lighter here, that means less density here and more dense here. That is what it means. Okay, so N2 is greater than N1. Okay, so therefore C1 must be greater than C2. All right, so the light travels faster in a lighter medium or in a medium which has got lower density. So therefore, it traverses a little bit of a further distance compared to Y2. The ray Y1 traverses a little bit of a further distance compared to ray Y2. Okay, so in other words, delta Z2 is therefore less than delta Z1. So therefore, if you now draw a front that where these rays were after a same amount of time delta T compared to this, you'll find that they have traversed different distances. As a result, their wavefront is no longer planar, but it exhibits an angle. Okay, so this is at T naught, this is at T equal to 0 plus delta T. Okay, so as you can see, that traverses different distances, and because of this gradation of refractive index, so you can imagine this to be like a candle plume also, or something else. That means it's lighter on the top and is more colder at the bottom. That is what it is. Okay. All right. So next is, now if you consider the same scenario, you will see this is a highly exaggerated view. Remember, the actual change is not that much. Again, we say that the refractive index gradient is less than 0. So it's a negative gradient. That means it's an increasing with the gradient is increasing with decreasing y. Okay. So in other words, again, look at this, that this is y2, this is y1. Okay. Now, if you see that this wave front, if you draw a parallel line to this, you'll see that it got tilted by an angle which is delta epsilon. So this is a highly exaggerated view. Remember, actual delta epsilon is a very, very low number. Okay, so the distance the wave moves in time delta t is given as, again, c into delta t, which is c naught by n into delta t. All right. Now, if you want to consider the refraction angle, you will find that it is basically the tan of this angle. So, but because this angle is very small, because that's what we showed, that n changes by a very small magnitude for a large change in density. So therefore, this is given as delta epsilon. So delta epsilon, now how do you calculate? You basically consider this value, which is c naught into n2 into delta t. So this is the distance that it traverses. Okay? And then you subtract out c naught by n1 into delta t, which is this particular distance that it traverses. So you basically take this out, so you're left with this basically, and then you divide it by the y, the delta y. So moment you do that, okay, you find that and also note that your delta t is nothing but your delta z multiplied by n divided by c naught. So once you do the mathematical manipulations, you'll find that this delta change with respect to the change in delta z, okay, is given by this expression. Note that this number n1 minus n2 is very small. N1 minus N2 is a very small number because we said that the refractive index changes by only minuscule amount. So therefore, this makes delta epsilon also very small to begin with. All right. So this is nice and easy. Now, if we go to a more of a limiting case where delta y goes to 0 and delta z goes to 0, the expression that we wrote earlier now can be reduced to, reduced to delta. This is the differential of epsilon with respect to z is given as 1 over n dn by dy. So dn by dy is the rate of change, is the spatial gradient of the refractive index divided by 1 over the refractive index, and this is the corresponding change in angle, in the tilt with respect to z. Now, recognize that though we have taken the variation in the y direction, there could be variation in the x direction, which is into the board, because the refractive index can change in that direction also. As a result of that, you see that your total change in epsilon in y, in the y direction, is given as the integral of the relative change of n with respect to y multiplied by dz, similar with respect to x. That means if you are considering the into the plane component, into the plane tilt of the wave front, that is also given in the same way, except that you have now a change in refractive index with respect to x, and in both these cases you are integrating it across the z. So if we have a 2D Schlieren of length L along the optical axis z, which is this, you are going to, if you integrate it out and assuming that this quantity are no longer dependent on the z, so what you have is basically L by n naught, okay, divided in multiplied by the gradient of the refractive index in the x direction and in the y direction. Now, this L that you see makes it a line of averaged type of a measurement because you are integrating it along the z axis. You are integrating out the effect in the z axis, and you are only concerned with the density gradient or the refractive index gradient in the x and in the y direction. So this is an important thing that you should note, that this is therefore along a length L along the optical axis. So more is the length L, you can see that more will be this epsilon y and epsilon x. So you need a larger optical path if you have to get more sensitivity out of your measurements. And also refraction is caused by the gradients of n and not by the overall value. So you can have a very dense medium and you can have a very light medium. Your Schlieren is not going to work if there are no inhomogeneities in the medium. So the medium has to be transparent and it has to exhibit inhomogeneity. When you have a homogeneous medium where there is no change in density, okay, this method is not going to work. Okay, so shock has a change in density, the candle flame has a change in density. So everywhere there is a slight change in density, that leads to even slighter change in the refractive index, and that leads to a little bit of a tilt of your wave fronts, and those tilts are basically given by these expressions, which are functions of the gradients of the refractive index rather than their absolute values. And the length scale, the length across which you are doing this measurement, also matters quite a bit. Okay, so now there is a classification of the optical methods. You have density based methods, okay, and then density based methods are basically of two kinds. One is the deflection of the light ray, which we just now saw. It can be, these measurements can be qualitative or quantitative. So under the category of deflection of light ray, you have shadowgraphy and Schlieren. And when there is a difference in optical paths, we get something called interferometry. The interferometry is quantitative. This deflection can be qualitative or quantitative. It will give you a picture, but in order to know exact information out of the picture, you need to do something else. So as you can see, if there is a disturbance like this and there is an incident beam of light, the light beams gets deflected, as we saw, because of the reason that there is an inhomogeneous media and the light gets tilted a little bit. Those tilts are the things that we calculated in here. Okay, these are the tilts. So when the Schlieren will measure those tilts and will give you some idea. Whereas on the other hand, the shadow graphs will measure there is a change in the intensity as well. So that will give you a shadow. So if you see the shadowgraphy is dependent on the second order derivative of the density with respect to x. So this change translates to a change to a gradient in n as well, because they are related in a linear fashion. And in Schlieren, of course, you have the first order derivative of the density with respect to x, y, okay? And essentially this also means with respect to, this is the gradient of refractive index with respect to x and y. Interferometry obviously will have just the absolute value, right? All right. So what we will do in this particular section, we'll stop here and we'll take it up in the next class. So as you can see that whatever we saw from a historical perspective also, that Schlieren, shadowgraphy, whatever you call, they depend on this deflection of light because there is a change in the medium. And because there is a change in the medium or the homogeneity of the medium, the rays get tilted by a little bit, very, very little. So if you have sensitive optics, you can still measure them. And we showed some examples that of a bullet, of a, of other types of things, of a candle. So we can do all this kind of stuff. So you can see that these are the shadow graphs, these are the Schlieren, these are the interferometry. They all, I mean, except the interferometry, they are all the gradients of the density, maybe the first order derivative or the second order derivative. They are never dependent wholly on the density as such. So you need a variation in density or a variation in refractive index. But the good part is that the density and the refractive index are related in a linear fashion. So that is the good part of the business, right? So this is a very initial discussion that how a Schlieren in principle can work. But of course, this is a lot of work. You need a very good quality mirrors and lenses, as you will see. That's why the historical perspective was so much important. Okay, all right. So we will see you in the next class.